Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. Our returning guest, Mark Holtzapple, is a professor of chemical engineering, Texas A&M University. I've had him on probably maybe 4 times already. He's working on a whole bunch of really fantastic projects that I think will transform how energy is used by society, how water is desalinated, etc. I had recently come across an article talking about how light can possibly vaporize water without the need for a significant heat. So we're going to be discussing that today and its possible implications. So welcome back, Mark.
Thank you. I enjoy these podcasts very much, so thanks for inviting me.
Yeah, no problem. Well, if you would, let's just recap what the article mentioned and where it came from. If you would, just do that, and then we'll get into questions about it.
Sure. This work was done at MIT, which of course is perhaps the most famous technical university in the world. And what they did was they shined light on the surface of water and found that the water would essentially leap out of the liquid into the gaseous phase, and that the energy required to do that was much less than the traditional 1,000 BTUs per pound of water evaporated. So they speculate that this perhaps could be used for desalination purposes and other things. For example, a cloud is basically liquid water, and the surface of the cloud is exposed to direct sunlight. So possibly this phenomenon occurs in clouds and therefore could be a component of weather. I'm quite sure that most models of weather do not include this effect because it's so new and unusual. But it actually might be something that has to be considered in future models.
Yeah, for people that don't know, what happens when water evaporates and or water boils, and then let's contrast it with this method.
Sure. I think everybody's probably experienced putting a pot of water on the stove and watching it boil. And what that means is that the so-called vapor pressure of the liquid exceeds the pressure of the atmosphere, which allows bubbles of gas to come up out of the liquid. So the idea is that every single water molecule in that bubble is steam. So their steam molecules are separated by large differences. And so you have to supply enough energy to pull apart the water molecules. So one way of thinking about water is it's liquid water, is that it's an interconnected web of water molecules. Just to get into the weeds a little bit, it's called hydrogen bonding. I think probably everybody knows water is H2O. The oxygen is really good at pulling electrons away from the hydrogen. So a single water molecule is polar. The oxygen is negative and the hydrogens are positive. And when you allow these polar molecules to contact each other, they align such that the hydrogens align with the adjacent oxygens. And so it's this web of interconnected molecules that are kind of glued together by these hydrogen bonds. So when you put a pot of water on the stove and you heat it up, what you literally have to do is every single one of those molecules of water has to be pulled apart and separated from its neighbors, which takes a lot of energy. And as I mentioned, a typical amount of energy is 1,000 BTUs to evaporate a pound of water. And so what kind of shocked me when I read this article from MIT is that they were saying they could pull water away from the liquid for much less than that. And so my skeptical ears were enlightened and came alive. And it's like, how could this be? I mean, I teach thermodynamics. How could you break the laws of thermodynamics? So I was very skeptical of the article. And fortunately, I kept an open mind and read further. And I do believe that what they have is true and real. But it was certainly raised a lot of questions in my mind when I first heard about it.
Well, first, it's a first question. So again, when water boils or gains enough energy to start evaporating, what bonds are being broken? Is it the hydrogen bonds, the intermolecular hydrogen bonds, or which ones are?
That's correct. So just to review basic chemistry principles, I think everybody who's taken high school chemistry has probably heard of covalent bonds. So in the water molecule, the H2O, the hydrogen and the oxygen are bonded together very strongly through what's called a covalent bond. But when you put a bunch of water molecules in close proximity to each other, as I mentioned, the hydrogen is a positive charge. It's lost its electrons, which were stolen by the oxygen. And the oxygen is rich in electrons. And so you get this polarity in the molecule, the water molecule. So if they get in close proximity to each other, they kind of align up so that the hydrogen of an adjacent water molecule aligns with the oxygen of the molecule of interest. And this becomes an interconnected web, kind of if you might think of it as a bunch of Velcro sticking the water molecules together. And so when you boil liquid water, you have to pull the Velcro apart. You have to, each individual molecule has to be ripped away from its neighbor in order to make steam.
If we model temperature, it's a curve. So in water, because of hydrogen bonding, would that mean that you would the body of water would reach a more uniform temperature faster, maybe through the exchange of phonons, between all the bonded water molecules, or, versus steam, let's say?
I've looked into phonons a little bit. I would not say I'm an expert in that topic. Liquid water has a pretty good heat transfer thermal conductivity, so that would indicate that the phonons are transferring energy pretty easily. But that's really a separate question from what we're talking about here. Thermodynamics doesn't care about rate, time. And so it simply says, I start with liquid water and I end up with water vapor. It doesn't care how long it took to go from liquid water to water vapor. A certain amount of energy was required to pull the molecules apart. So the phonons and heat transfer is really a separate issue from the thermodynamics. So rate and thermodynamics are two separate domains.
I don't even know if this is possible. What is on a per molecule basis, what would be the amount of energy required to break, a hydrogen bond?
I haven't memorized that number, but the 1,000 BTUs per pound is, you could use Avogadro's number and get that pound into individual molecules, but I haven't done that, so I don't have a good answer for you off the top of my head.
No problem. So again, when water evaporates, what'll break first is what the intermolecular hydrogen bonds, and individual water molecules will volatilize off, or what would it look like?
That's right. So at kind of ordinary temperatures, I think most people know water boils at 100 degrees Celsius at 1 atmosphere of pressure. That's not particularly energetic. So it is enough energy to break the hydrogen bonds and release the water molecules from the liquid into the vapor. If you go to really high temperatures on the order of 1,000 degrees Celsius or 2,000 degrees Celsius, at that point, it's so energetic that the water molecules actually break apart. The covalent bonds will break down. And that's actually a way that people consider to split water, so that, people want to break down water and make it into hydrogen and oxygen, the hydrogen being an energy carrier. And one of the ways of doing that is to expose water to super high temperatures, and it simply breaks down, again, enough energy that the covalent bonds are broken. It's a pretty brutal process, as you might imagine, and it's not generally what people consider if they want to break down water into hydrogen and oxygen. They usually do it using electrochemistry rather than thermal processing, which again is very brutal.
Okay. So what's happening under the MIT situation? So light of a certain frequency or wavelength is hitting the water, and what bonds is it breaking?
Yeah, so what it's doing, it's still breaking the hydrogen bonds between the molecules, but it doesn't separate each molecule from its neighbor. It basically kicks out chunks of water. So what's ejected into the gaseous phase is not individual water molecules. It's chunks of water. And so that's why it takes less energy to separate the water to get it into the vapor phase, because you're not separating every molecule. Again, using the Velcro analogy, you're not pulling apart every single molecule from its neighbor. You're just ripping out a chunk of water molecules.
So what's the size distribution of the chunks? Like how many molecules? Has that figured out by MIT?
I'm not sure that maybe they calculated that. I didn't investigate it enough to give you an actual number. I was just trying to figure out whether this thing has merit or not. I mean, is it true or not? And so I was more interested in how could you, quote unquote, violate the laws of thermodynamics using light, because thermodynamics is thermodynamics. It doesn't really matter where the energy comes from, whether it's light energy or thermal energy, to separate the molecules. But what I learned when I got into the details is that you were not separating each individual molecule. You were tearing out chunks from the surface of the water, and that's the mechanism.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
If you were to use this, how would you tune it? What would be an ideal size of the molecular cluster that you would cleave off? And, how could you evaluate the geometry of what is cleaved off to find the fewest number of points to break it off? Like, what could be done there?
Well, that's an interesting question. So really what you would try to do is say, what's the minimum amount of light energy I need to rip out the chunks? So we do know, about how much energy there is from the hydrogen bond. And so we could, if we know how much water we've separated based on the amount of light energy, we can actually calculate how many bonds were broken. And then you simply look at, well, I broke up this many bonds, but this many molecules are now in the gas phase. And so you could actually calculate based on that how many molecules, or estimate the amount of molecules in the surface. Now that calculation would have to assume that the efficiency is 100%, that all of the light energy, it goes into breaking the hydrogen bonds. And that might not be true, actually. I mean, it's probably not true. So it makes it difficult. You'd have, if you really wanted a definitive number, you'd have to actually look at the size of the water droplets that are ejected. What will happen when a chunk of water is emitted from the surface, it will form a sphere. That's the lowest energy state. I think most people are familiar with something called surface tension. That's why bugs can walk on the surface of water. So that what will happen is this kind of skin of water molecules will make it form into a sphere. So what you'd have to do is get the size of these nano water spheres that are emitted from the surface of the water.
Which, I guess you'd want the most amount of surface area available. So if you had atomized water, made it a very, very fine mist, and then had a light source or laser source, shining through it, I guess give you the most.
Yeah, absolutely. That's how you would do it, is look at the light scattering, and the scattering pattern should give you some information about the size of the water droplets. The word nano is very popular. So basically what you're making is nano-sized water droplets that are ejected from the surface of the liquid water. And then the next question, of course, is gravity simply going to let them drop back down into the liquid water, and then you've lost all that work that you just put into it? Or can you kind of sweep away the liquid droplets and keep them in the gas phase? So that becomes a, kind of a practical limitation or issue to address.
Yeah. Well, if you struck a body of water with one photon and you broke, let's say, one hydrogen bond, how quickly would it reform? So if the light hit the water in a short enough time frame, I guess you would overcome the ability of the water to reconstitute itself as water, and then it would, come off in chunks, as you say. There's probably a time component too.
Yeah, I think you're exactly right. That, as you say, if a photon hits the bond, the hydrogen bond, it would want to reform, and as though nothing happened. But if you hit it with enough photons all at once, it doesn't have time to reform, and it kind of blows out as chunks. Before I was a professor, I was in the Army, and there's a process called spalling. So if a shell hits the outside of a tank, what can happen is chunks of metal will spall off the interior of the tank, and that's one of the ways that people in a tank would die, from the ball. And so in a sense, that's what you're doing here, is you're exposing the surface of the water to a lot of energy in a very intense form, and the spall is emitted from the surface in the form of these nano-sized chunks of water.
So if you were in a lab and you were heating up, an amount of water, and you also hit it with, let's say, a pulsed laser at the right frequency, do you think you could get the water to boil at a lower temperature or with less energy input? Could this be a helper for a process like that?
Well, I guess it comes down to nomenclature. What do you mean by the word boil? So if you're truly boiling water...
If I'm going to make steam, for some industrial purpose, I'm heating up the water, but I'm also, again, hitting it with a laser. Would that help it along? Would I have to put in less energy?
Not really, because you're not really making steam. You're making a fine suspension of nano-sized water droplets that are suspended in air, or that would be typically what people would assume. So it's not really steam, it's just nano-sized water droplets that have spalled off the surface of the water.
Well, if you had it in a contained volume, and again, let's say the laser went through the body of the water, would it slow down maybe even the boiling process? Like you would create temporarily, unbelievable amounts of holes in the lattice, the structure of the water. It's not really a lattice, but, in the structure of the water with hydrogen bonds being broken. Would that help contribute? Would that add surface area to the water and allow it to be boiled again more quickly, more effectively, et cetera?
I'm thinking about your question. I'm not sure I can come up with a definitive answer, because certainly laser light can be added more quickly than heat. So heat really is transferred through a wall of a container. So the metal, we think of metal as a good conductor, and generally it is, but compared to the amount of heat necessary to boil away water, the metal wall actually is a restriction. It's hard to supply enough heat through the metal to satisfy the need of energy to boil. So yes, if you had a laser that could focus directly on the water and not have to go through the wall, you could vaporize water much, much more quickly. You think about a military laser that they might use to shoot down drones or missiles. There's quite a bit of energy in that beam. And if you directed it at the surface of water, it would very, very quickly blast apart the water much, much more quickly than you could possibly add heat through the metal wall. But the second part of the question is, from a practical sense, is that how you'd want to do it? Lasers are very expensive. They run on electricity, not fuel. Electricity is a pretty expensive form of energy. And so you'd have to ask the question, why do I want to do this so quickly? Yes, you could. If you had let's say a military reason to blast apart water very, very quickly, a laser could do it, but most industries don't need things to be done that quickly. They want things to be done more efficiently. And that actually, I think, leads to an important thing to talk about in this context. So our colleagues at MIT have done this very interesting work. I have to compliment them. This is very, very interesting. But then the second question, that it's interesting from a scientific standpoint as a way to make nano-sized water droplets. It's very, very interesting. But then when you put on your engineering hat, you have to start asking questions. Okay, what would I do with this information in a practical way? How would I use this information? So there's really two separate things. So a scientist can say with pride that I discovered a new phenomenon and I published a paper and described this phenomenon, and I've now added to mankind's knowledge. And from that perspective, that was a great success. You learned something that has never been learned before. It's been documented in the scientific literature, and it now adds to the body of knowledge of mankind.
Sure.
But engineers, though, have a different task. Think of this kind of infinite body of knowledge that people have been discovering over many, many centuries. What an engineer does is kind of picks from that body of knowledge and says, what particular pieces of knowledge are useful from a commercial and, let's say, an industrial standpoint. And that usually is a small subset of mankind's knowledge. I don't have an exact number, but maybe 1% or 1/10% or some number like that of all of mankind's knowledge is actually useful for something.
Well, I'm trying to find these applications right here during the interview. Why not? That's why I'm asking.
Of course. I mean, that's what usually, just as a sidelight. I mean, let's imagine that you're a bioscientist and you discovered something new. A person might ask, could you cure cancer with that knowledge? And maybe the answer is yes, maybe the answer is no. But generally what people want to know is, okay, you've done this wonderful science. How does it make my life better? How does it improve mankind's position in the world? And that frankly is where I struggle. So go ahead.
What comes to mind here is, how would this affect water-based chemistry? So let's say you are pulsing it with a laser, or you just have sunlight incident on it, by forming these nano droplets, maybe within the body of the water or at the surface. How would that change the chemistry of what you're trying to do in water? That might be something, that'd be a whole avenue to explore, just as a for instance.
Yeah, it's a great question. One of the things they talked about was using it for water desalination, which of course is a huge human need. We keep having more and more people on the earth, but we're not making more and more potable water. And that's, of course, what motivates one of my research interests is to learn how to desalinate water more effectively, efficiently, economically than the current technology. So if I look at it from that perspective, the very first question that I would ask is, okay, if you have salt water and you zap it with these lasers or sunlight, the chunks of water that come out, do they still have the salt in it? It's not obvious to me that when the chunk comes out that it only lets water come out and not the salt. Going back to this bonding situation, if we think of salt water or seawater as sodium chloride, the sodium is a positive charge and all the oxygens in the water align around the sodium, and the chlorine as a negative charge and all the hydrogens align around the chlorine. And so when the laser zaps the water and the chunks come out, frankly, I would assume that the sodium and chloride comes with it. And so you really haven't separated the water, the H2O, from the sodium chloride. Now, I'm only speculating. I don't know. I haven't read about whether that experiment has been done or not. But that would be, if you're talking about it from a practical sense, that would be the first question that I would want answered is, if these chunks are coming out, why is it that the sodium and chloride would stay behind in the bulk liquid and only the H2O would come out? And I have trouble off the top of my head explaining why that might happen. So further experiments would be needed to show whether my concern is valid or not.
What about for other liquids that don't have hydrogen bonding, or let's say, in an engine, you want to, you'd atomize the fuel essentially and put it into the compression chamber.
You're so clever in your questions. That's a very interesting question. So yes, in an automobile engine, like in a diesel engine, what they do is literally spray diesel fuel through a high pressure nozzle, and it's this fog of diesel that ignites. And their time is a factor because you have only so many milliseconds before you have to repeat the process again. And so if one were to let's say have a laser beam that goes into your piston and blast the fuel, I could see that doing a better job of atomizing the fuel and maybe reducing pollution and maybe getting a little bit more fuel efficiency. So that would be very, very interesting thing to look at, and it very well could be that you have to look. Substances have an absorption spectrum, and so you'd have to tune your laser to the frequency where the diesel fuel absorbs, and then zap it, with a high amount of energy, and that it would literally explode the droplets and allow them to burn. When I say explode, what I mean is fragment them into tinier droplets that can then burn with the oxygen much more efficiently. So that's a very, very interesting idea.
Yeah, and I figure there's always some water component to any fuel mixture. You probably can't get rid of it all. So, even if it only affects the water component, maybe it
Well,
combust in a different way, what would that do?
Yes, there is some water in fuel. When I was in the Army, my specialty was fuel, and so there's always this concern about the water getting into fuel. What can happen is if you have too much water in the fuel, if let's say your tank of fuel gets cold at night and the water drops out, usually the engine draws the fuel from the bottom of the tank, and so what you'll be doing is drawing water rather than fuel, and you're trying to start your engine and it won't start because your fuel engines can't run on water. So what I'm getting to is that people that manage fuel supplies are very concerned about having water in fuel, and they go through a lot of effort to minimize water. So there's not normally very much water there. Now, having said all that, there is people that may know a little bit of history know that during World War II, they would spray atomized liquid water into the piston engines used by the aircraft. That had a number of beneficial effects. It would cool at the intake so that you can get more fuel in there. And so in principle, if you purposely sprayed water into your engine, this could, in theory, in principle, bust up the water into finer and finer droplets so that it enhances this effect. So that would be a very interesting potential application. You could envision a fiber optic cable going to the head of your engine and blasting intense laser light into the engine as it's operating. All this is speculative, but it's certainly something fun to think about.
Yeah. Well, I'm trying to think about applications based on some of the research that you're already doing. Maybe this could, make it work even better, whatever you're working on. And so that's why I mentioned it.
Yeah, that's a very, very interesting idea. But I guess getting back to my earlier statement, so the job of scientists is to understand more and more about nature, and a scientist is successful when they discover new phenomena that have not been documented before, and it's now encoded in papers that are in the literature. And I like to believe that if mankind survives for thousands and thousands of years, that our literature will survive with us, and we're constantly adding to mankind's knowledge. And then the role of an engineer is to sift through that knowledge and say, oh, here's something I could make money with. And that's exactly what you were doing with the speculation about the engine. Is like, okay, how could we use this information in a practical way? And I would say that's the fun of engineering, is taking interesting phenomenon and trying to bridge into the commercial world.
Yes.
So I don't know, of your listeners, how many people are engineers or were thinking about becoming engineers, but it's a wonderful profession. I love being an engineer because you can learn about the physical world and then apply that knowledge in a way that helps mankind, humankind. So I think there's hardly to my view, anything more interesting and fun than doing that.
Well, I have a bachelor's in chemical engineering, but it's like 25 years ago. But it helped me understand order of magnitude and make approximations pretty quickly, ballpark estimates. And, I understand how to break a problem down into pieces and solve the pieces. So it's been very useful for me in my life, even though I'm not doing engineering like you are.
I agree. Just as an aside, years ago, I learned that Japan graduates 3 times more engineers than they need for industry. And people might say, well, that's wasteful. Why are you doing that? And what they find is that not only are these engineers needed in industry, but they're also used in business and finance and so forth. And the reason is that when you go through the rigors of an engineering education, you've learned how to break a problem apart, just as you described. You've learned about logical and sequential thinking, critical thinking, and you have to be very dedicated to get an engineering degree. We just don't hand them out. You got to work really, really hard. So you have a really good work ethic if you've earned an engineering degree. And so Japan exploits these, I would say, excess engineers that are educated above and beyond what industry needs. And they employ them in all kinds of areas that are not directly related to engineering. I
think because they love Kaizen, they love continuous improvement, small little improvements to a process over time. So I think that fits well with an engineering mindset, is my guess.
It does. And you'll often find leaders of industry have an engineering degree. And so this logical, sequential thinking, concern for details also translate well into the business world. And so I think business, when you let's imagine you're trying to hire a CEO of a company and you see that one of the candidates has an engineering degree, that signals that that person has been able to withstand the rigors of an engineering education. They know how to be quantitative and sequential in their thinking. There's just a lot of good things that come out of the engineering process. And again, that's why I love being an engineer. I love teaching engineering. I think that for me, engineering is a calling, and I want to share that with other people.
Yeah, that's fantastic. So, I guess going forward, you'll think about this new phenomenon discovered by MIT and, see how it can dovetail with what you do. For people to find out more of the work that you're doing, the projects you're working on, I think a lot of them are fantastic. Maybe you can mention the ones you're working on, and then where can people find out more about your work?
Mostly I publish in the area of biomass conversion. So when I was in high school, we were going through the energy crisis, and I purposely became a chemical engineer so I could learn how to convert biomass into fuels. America has really good, strong agricultural system, and we can grow lots of biomass. We still do that, and we just need to figure out how to turn biomass into fuel, and we do that commercially. Corn is turned into ethanol. About 10% of gasoline is actually ethanol from corn, and so I wanted to make that into more than 10%. I'd like to basically have 100% of our fuel come from biomass. If we can achieve that, that means our fuel does not contribute to global warming. And the explanation of that is that when you burn fuel that comes from petroleum, that carbon used to be under the ground in an oil well, and now it's in the atmosphere. So that keeps putting more and more carbon into the atmosphere, which contributes to global warming. If you take a plant and convert it into fuel, the plant got the carbon from the atmosphere. And when you burn that fuel, you just put it back in. So it's just a cycle. The carbon goes around and around and around and never accumulates in the atmosphere. So there's hundreds of papers that I've written over the decades on this technology for converting biomass into fuel. I have also a strong interest in desalination. When I was in the Army before being a professor, I did some research in water desalination, and that's one of the challenges that faces mankind is resource limitations. Just as an aside, this comes to mind. China has control of a river. Let me put it this way. There's a river that originates in China and it ends up going to India. And for centuries upon centuries, India has relied on that water to supply its population. If China decides that it's going to use that water for its own purposes and the water never makes it to India, then literally millions of people could be without water. That very same thing is happening potentially in Egypt. I think everybody has heard of the Nile River and its essential role in supplying Egypt with water. Well, Ethiopia is building a huge dam on the Nile River, and so it's possible that not as much water will actually end up in Egypt as has historically been the case. So Egypt has to worry about, okay, what's going to happen if we don't have the water that we used to? I've seen articles, they have actually threatened to blow up the dam. So that gives you a sense of how strategic water is. So if we can help people get along better by saying, look, there's plenty of water, we can desalinate it economically. You don't have to go to war over water. We've got that covered. Again, that's something that I think would be very helpful to mankind.
Yeah. And where can people find your publications and see your most current work?
Well, I think you can just use Google and type in the name Holtzapple and put a keyword like water desalination or biomass or whatever, and you'll start finding articles. Some other things I'm doing that have not been published, but I'm quite consumed by it, is trying to come up with ultra strong materials that you can build buildings out of. Concrete is the second most widely used material. Put it this way, the second most produced material that humans make is concrete. The number one is water. So I've turned my attention to number two, concrete, and trying to figure out how to make it stronger and capture CO2 and come up with new ways of building buildings that make them go up faster, so that can help relieve some of the pressure on housing. My mind kind of goes 1,000 different directions, but always trying to figure out how to make the world a better place. So that hasn't been published yet. A patent has been filed, but nothing in the public domain yet.
Okay. Well, very good, Mark. It's always great to hear from you. I just feel like you're a really good communicator of these concepts. So it's easy to talk to you about this than, perhaps some other engineers I've spoken to. I think engineers in general also are better communicators of science concepts sometimes than pure scientists. So I appreciate you coming back on the podcast yet again.
Well, I appreciate the compliment, and I appreciate that very much. I am a dedicated teacher and do my best to explain these complicated concepts in ways that essentially a high school student can understand it. And I love doing that. Again, I believe strongly that engineering is a calling, and it can be very, very hard to learn engineering if it's not taught properly. So I've really worked hard over the many, many years to try to take complicated ideas and make them as simple as possible. So I appreciate your nice compliment. Thank you so much.
Excellent.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.